So 8.6 is focusing on graphs of quadratic functions. So graphs of functions, because they pass the vertical line test, that are quadratic, are coming from a quadratic, meaning the highest exponent is 2. Again, they will make that parabola shape. So when your a is positive, meaning greater than 0, your parabola is opening upward. We talked about that in lesson 8.5, which makes the vertex a minimum. When a is less than 0, meaning when a is negative, your parabola open downward, and therefore your vertex becomes a maximum. So there's often questions about, is your vertex a minimum or a maximum? So that's how you determine it. It's based on, does it open up or down, because then it's a min or a max. To find the actual value of a vertex, you have the vertex formula. When it's in standard form where you have an A, B, and a C, it's the opposite of B divided by 2A. So it's not always negative, it's the opposite of B divided by 2 times A. And then you plug that into the X there and there in your quadratic, follow order of operations, and that will get you the Y coordinate for your vertex, because your vertex is a point. So your X is found that way, your Y is found by plugging it in and finding the Y that goes with it. When it's in vertex form, it's just that HK, the opposite of what's showing there next to the X before, in the parentheses before it's squared, and then keep the K, whatever is being added or subtracted, just the way it is. So this is kind of a nice summary about the two different forms and how to handle some of the key points. Vertex being very, very, very important for graphing on XYZ, but also just in general, because we want to see that place where it is at its max or min in real life oftentimes. Another important thing is the intercepts. This will be very important moving on in math, in pre-calculus and calculus, etc. But also in this class. It's related to where your y is 0. So when we were solving quadratics, we set them equal to 0. It's kind of like the y being 0. We factored when possible and solved it that way. You can also use the quadratic formula. You can also use the square root method, depending on, if you want to complete the square, you can always do it. Or if it's just x squared and no x's, you can also use the square root method. If it's in vertex form, you set the y equal to 0 also, and then you can subtract the k, divide by the a, take the square root, and then add the h. So in other words, you can isolate the square part and then take the square root, or you can follow order of operations and rewrite it into standard form, and then you have those 3 options like you did before. X-intercepts are also known as the zeros because it's when the y is 0, and the solutions, because it's what makes the solutions to the quadratic when it's 0. It's also known as the roots because you end up taking a square root if you use quadratic formula. I believe those are the reasons why. At least that's how I remember them. And then y-intercept is when your x is 0. So you just plug in 0 for x in either format, it'll work. Just follow order of operations. What's kind of neat, just like with lines, y equals mx plus b, your last value, your constant, is your y-intercept. So it's going to be 0, c. But the idea is just know that for a y-intercept, x is 0. That will work for any shape you have. Parabolas, lines, circles, ellipses, hyperbolas, square roots, any shape. And then axis of symmetry sometimes gets asked about. You can often just graph it and see it visually. It is always a vertical line when these parabolas are opening up or down. You'll learn at the end of the course and in pre-calculus what happens when your parabolas are opening to the right or left. Basically, the x and y switch places. In any case, the axis of symmetry is going to be the vertical line, so x equals, and it goes through your vertex. So that's why it's still negative b over 2a. It's the same formula. So when you find your vertex's x coordinate, the equation for the line where x equals that is the axis of symmetry. Similarly, here's the x of your vertex, so it'll go through that for it when it's in vertex form. You can take something that's in standard form like this, y equals ax squared plus bx plus c, and rewrite it into vertex form. The benefit of that is it's really easy to graph from vertex form. You plot your vertex and you use that pattern of 1, 1, 2, 4, 3, 9 if the a is 1, or multiplying the 1, the 4, and the 9 by your a when a is not 1. It's harder to graph these. You'd have to find the vertex using the vertex formula, or you could use the intercepts. You could see if it's factorable. They won't always be. So it's this is a nice way of doing it. It's also great practice on completing the square, and the square root method can also be discussed through this process. So completing the square, we got our x terms by themselves, so we subtracted 10, so y minus 10. Before you used to have a 0, now you have a y because you're writing the equation. So then I complete the square of the part that has the x's, so I take half and then square it, the b over 2 squared, the completing the square method. And so I get -3, and then when I square that, I get +9. Then I rewrite this in its factored form as that perfect square. It's x minus 3. You can see the diamond here, the x method here, or you can always just take half of your b. And then I simplify -10 plus 9 is -1. And then I'm trying to get it into vertex form. So I'm trying to get it to look like this, y equals a x minus h squared plus k. So I want to get the y by itself, so I'm going to add 1. And I do want something squared plus something or minus something. And it could be that it's 0, but the point is that I don't want to keep this in this format. I do want to put it in the parenthesis format and just stick this on the end. I cannot combine it with this because this is being squared. That would be not following order of operations. So it's this squared plus 1. Again, your vertex is opposite and then same, and your a is the number in front here, so invisible 1. There's a couple more here. You guys are not going to have to worry about when a is not 1. And so, oh wait, in this context you do, sorry. So factor out your a so that it ends up looking like that factored form. You want the a out in front here, so you want it factored out. So get your x's by themselves, factor out the a, then complete the square, half squared, and then when what you do to one side, you do to the other. Remember, you're actually doing 3 times 9. You have to pay attention to the distributive property. So again, isolate x terms, factor out the a, fill in the blanks. Don't forget about the distributive property when you fill in your other blank here. And then just like before, get your y by itself and rewrite this as a perfect square. And there it is in vertex form then. Vertex being opposite of what's in the parentheses here, and then the same for what's outside, and the a is the part in front. Here's just another practice about, getting the x terms by themselves, factoring out 2. So this -4, when I factor out a 2, is 2 times -2 is the -4. So just be careful that you are factoring out of all the terms, and that you pay attention to the distributive property and add, in this case, 2 times 1, 2 to the side as well. Simplify, get y by itself, and then the vertex opposite same and the a. So the next couple slides are on graphing more from standard form and just all the different components that we've talked about. So it's called the 411, all you need to know. So here it's in standard form. So you can quickly talk about the y-intercept by just doing 0, your c. So this is a template. The gray part is all a template, and I just used this as an example to illustrate how this template works. So because it's in standard form, if you want to find the vertex, you can use the vertex formula. And here it is as an ordered pair. X is -b over 2a. The y is when you plug that in to your function. So it's written in kind of function notation format here. You can also complete the square, but I want to practice this a little bit. So x equals negative b over 2a. So that's going to be x equals the opposite of negative 4, so 4, over, or divided by 2 times your a, which is 2. Simplify, you get 1. You're going to plug that 1, your x is now 1 for your vertex, plug that 1 in for your x's, and find the corresponding y. So you're going to do 2 times 1 squared minus 4 times 1 minus 6, following order of operations. So there it is. Order of operations, you're going to square first, you're going to do your exponents, then you're going to do your multiplication, and then you get to do your addition or subtraction. So it's 1, negative 8 for your vertex. That's the main point of this particular lesson, is just how do you use the vertex formula. So there's an example. We also have over here how you can factor it, factoring out a GCF of 2, and then this is factorable to x plus 1, x minus 3 times that GCF of 2. That is a nice way to be able to find intercepts, right? When y is 0, you can find your x-intercept by just setting the factors equal to 0. So that's where your x-intercepts would be. If that doesn't work, there are other ways to find the x-intercepts. Again, set it equal to the y equal to 0. You can solve a quadratic formula. You can complete the square. Okay, so this is just vertex form. Once you have the vertex, you can put it in vertex form. You steal the a, you do x, you do the opposite, squared, and then keep that the same as it is. So I graphed those just to give you an idea, and you can see that the a being 2, from my vertex, when I go over 1, I go up 2. You can see the y-intercept there and the x-intercepts there. It all matches up. And if I go over 2 from the vertex, because the a is 2, I'm going to double my 4 and go up 8. And there it is. It all matches. So it's kind of nice to be able to check all your work. All right. So here's another example in standard form. This one was not factorable. Nothing multiplies to 3 times 5, 15, and adds to negative 4. So I can't put it in factor form. My y-intercept, when I plug in zeros for my x's, is 5. I did the vertex formula on this one as well. This one ended up being a fraction, so you can see some work with fractions here. Getting common denominators, simplifying, then the denominator was already 3. I made that one 3. And so you get not the nicest point to graph, but I just wanted to also work on the fact that sometimes you don't get nice integers. And so if I were plotting that, I just do it approximately. I go to about 2/3 of 1, and then 11/3. I can count up 1/3, 2/3, 3/3, 4/3, 5/3, 6/3, etc., or recognize it's 3 and 2/3. So I go up 1, 2, 3, and 2/3 of the way. And you can write the vertex form from that. Looks like I didn't do that, and the reason I didn't is because, actually, let me get a text box, is because it's not as nice with the oops, it's not as nice with the a not being 1. I'm trying to get my mouse. What was the a on this one again? It was the a was 3. So y equals 3 x minus 2/3 squared plus 11/3. Just make sure that it has the correct preview, that you type it in correctly, that you put parentheses where you need to, etc., so that it interprets things correctly. It'll do the division before the addition, so that should be fine. Okay, I'm gonna clear that. So here, this one, as I said, oops, could not be put in factored form. So when I do my x-intercepts, I'm gonna have to solve it by quadratic formula. I like to find the discriminant first. And so b squared minus 4ac, the part underneath the square root of the quadratic formula, plug things in parentheses, and did my order of operations. And because it's a negative, it means you're going to have some imaginary numbers. So I already know at this point that my graph is going to be floating. It's not going to cross the x-intercept. And because of that, I can't plot this. There is no x-intercepts, as you can see when I graphed the parabola here. So I right now only have that y-intercept in the vertex. I need some more points. If you're doing XYZ, as long as you have the vertex and one other point, you would be fine for graphing it. But by hand, and to have a better understanding of graphing quadratics, when you move on beyond this class, when you're not just dealing with XYZ, when you're actually taking a test on ground, it's good to recognize how to handle those situations and know how to find all the key components. So I needed another point, ideally something on the right. So I can try plugging in x of 1 and seeing what I get, or an x of 2. I don't want to go too far away because then it'll go off my graph. But 1 and 2 both ended up being rather nice when I did order of operations and simplified. So imaginary gives you no x-intercepts. All right, here is another one. I'm gonna talk about this again. It did not factor, so I use quadratic formula. And when I go to plot these, I'm gonna have to find the approximation to plot it on a graph. So I can take out my calculator and type in -2 plus the square root of 10 and then -2 minus the square root of 10 and plot those approximations. If you were at, or state this as an exact, comma 0, if you were having to state what the x-intercepts are. Often we don't graph them unless needed when it's approximations, but it does in fact make everything match, and that's the beauty of all this. All of these different concepts and all these different components have to come in and match up with each other. So I had found the vertex -2, 5 by doing the vertex formula here, watching your order of operations and your signs. I had the y-intercept, and that would be enough for x, y, z. But you can also see if you plug in some other points. If you plugged in -1, you'd get something there, or if you plug in -3 there. If you plug in -4, you'd get exactly 3. Those are symmetrical because, again, parabolas are symmetric about the line that goes through the vertex. So that's 8.6.